In this module, you will learn about the periodic trends and the physical properties of elements in the periodic table. A gradation in their physical and chemical properties is attributed to the arrangement of elements with respect to their electronic configurations. In this particular module, you will learn about the periodic trends in physical properties such as atomic radius, ionization enthalpy, electron gain enthalpy, and electronegativity. The first important physical property is atomic radius. Atomic radius can be defined as the distance from the center of the nucleus to the point up to which the density of electron cloud is maximum. Measuring the actual atomic radius is a difficult task for two reasons. First, the size of an atom is of the order of 1.2 angstrom or 1.2 multiplied by 10 to the power of minus 10 meters, which is too small to be precisely measured. Secondly, the electron cloud surrounding an atom does not have a well-defined boundary, which again adversely affects the precision of the measurement. However, it is possible to estimate the radius or size of an atom by knowing the distance between the atoms in a combined state. Depending on the nature of bonding, atomic radii are of three types. They are covalent radius, metallic radius, and van der Waals radius. Let's learn about each of them in detail. Covalent radius is a general term which is used in reference to non-metals. A covalent radius is 1/2 of the distance between the nuclei of two atoms, held together by a covalent bond in a homodiatomic molecule. For example, the internuclear distance between the chlorine atoms in the chlorine molecule is 198 picometers. Therefore, the radius of a chlorine atom is the half of this distance, which is 99 picometers. For metals, we use the term metallic radius. Metallic radius is half the internuclear distance between the centers of the nuclei of two adjacent metal atoms in a metallic crystal. For example, the distance between two adjacent copper atoms in solid copper is 256 picometers. Therefore, the metallic radius of copper is 128 picometers. Atomic radii of both the types, covalent and metallic, are usually measured by X-ray or by other spectroscopic methods. Let us now see the variation of atomic radii across the periodic table. Generally, atomic radius decreases across a period and increases as we go down a group. The table lists the atomic radii of few elements from the second and third periods of the periodic table. The decrease in atomic size across a period is due to the increasing effective nuclear charge with increase in atomic number. Nuclear charge is the net positive charge experienced by an electron of an atom. The effective nuclear charge varies with the proximity of electrons from the nucleus. This is because electrons in the inner orbitals shield the electrons in the outer orbitals from experiencing the full nuclear charge. For example, the valence electron in cesium is shielded from the nucleus by the inner electrons. As a result, the valence electron experiences a net positive charge that is less than the actual charge. Across a period in the periodic table, as we move from left to right, the nuclear charge increases by 1 unit in each succeeding element, while the principal energy level remains the same. As a result, the effective nuclear charge increases, and the electrons in the valence orbital get more strongly attracted to the nucleus, reducing the size of the atom. Down the group, the atomic radius increases with the atomic number. As we move down the group, a new energy shell is added to each succeeding element. In other words, the principal quantum number n increases down the group, and the distance between the valence electrons and the nucleus increases. As a result, the shielding provided by the electrons in the inner energy levels becomes more effective, especially if the inner orbitals preceding the valence electrons are full, as in the case of alkali metals and halogens. Therefore, the size of the atom increases down a group. According to the atomic size trends explained so far, the noble gases should have the smallest sizes, as they are the last elements in each period. However, the atomic radii of noble gases are not considered here. Noble gases, being monoatomic, have very large non-bonded radii values. Hence, the radii of noble gases should be compared with the van der Waals radii of other elements rather than the covalent radius. Van der Waals radius is half the internuclear distance between two non-bonded neighboring atoms or two adjacent atoms belonging to two neighboring molecules of an element. Van der Waals radii are usually larger than covalent or metallic radii. The radius of an atom changes when it loses or gains an electron to form an ion, and the resultant radius is called ionic radius. Ionic radii exhibit the same trend as the atomic radii. When an atom loses an electron, it forms a positive ion called cation. The radius of a cation is always smaller than its parent atom because, while the nuclear charge remains the same, the number of electrons is decreased. This results in increase in the nuclear attraction on the valence electrons, leading to decrease in the size of the atom. For example, the atomic radius of sodium atom Na is 186 picometers, whereas the ionic radius of sodium ion Na+ is 95 picometers. Similarly, when a parent atom gains an electron, it forms a negative ion or an anion. The addition of one or more electrons results in an increased magnitude of inter-electronic repulsions among the electrons and a decrease in the effective nuclear charges. Therefore, the size of an anion is larger than that of the parent atom. The atomic radius of fluorine, F, is only 64 picometers, whereas the ionic radius of fluoride ion F- negative is 136 picometers. Clearly, the variation between the atomic and ionic radius depends on the effective nuclear charge. This is why the ions belonging to isoelectronic series have different ionic radii. Isoelectronic species may be defined as atoms and ions which contain the same number of electrons but differ in nuclear charge. Within a series of isoelectronic species, as the nuclear charge increases, the force of attraction by the nucleus on the electrons also increases. As a result, ionic radii decrease. For example, N-3, O-2, F-, Na+, Mg+2 and Al+3 ions have the same number of electrons, that is 10. However, their radii would be different because of their different nuclear charges. As cation with greater positive charge has smaller radius and anion with greater negative charge has larger radius, the order of ionic radii among the isoelectronic species increases in the order as shown here.